In this video, we'll be analyzing paired sample data. We'll look at the methods to determine whether there is a correlation or association between the two variables and whether this association is linear. We say there is correlation between two variables if the values of one variable are somehow associated with the values of the other variable. A linear correlation exists between two variables when there is a correlation between them and the plotted points show a pattern that can be approximated by a straight line. For example, if we look at these two graphs, we can see that there is a linear correlation between the two variables. In the first graph, there is positive correlation because the pattern is increasing, shows an increase from left to right, and in the second graph there is a negative correlation because the pattern shows decrease from left to right. In the third graph, there is no correlation between the two variables, and in the fourth graph we can see that there is some correlation, but the correlation is not linear. To measure a strength of linear correlation between two variables in the sample, we use linear correlation coefficient R. For a linear correlation, we can identify an equation of a straight line and use that equation to predict the value of one variable from the value of another variable. For example, police sometimes use footprint evidence to estimate the height of a person. Here's some examples of the measurements. Using this data, can we confirm that there is a relation between a person's footprint and a person's height? And if we do confirm that there is a relation, how do we use it to develop a formula to predict a person's height based on the person's footprint? In this video, we will learn how to find a linear correlation coefficient R, how to interpret it, and how to test a claim that there is a linear correlation between two variables in a sample, and how to predict the value of one variable based on the value of another variable.
To explore sample data, we use scatterplots. A scatterplot, also called scatter diagram, is a plot of paired x and y coordinates quantitative data with a horizontal x-axis and a vertical y-axis. The horizontal axis is used for the first variable x and the vertical axis is used for the second variable y. Here are some examples of the scatterplots. Linear correlation coefficient R has the values between -1 and 1. If R is close to -1 or close to 1, there appear to be a correlation. If R is close to -1, then there will be negative correlation. If R is close to +1, there will be positive correlation. If R is close to 0, there does not appear to be a linear correlation. Remember the graphs from the beginning of the video? The first graph represents positive correlation because the line has a positive slope. The y values increase as x values increasing. And the second graph has negative correlation, negative slope. The y values decreasing as x values increasing. The third graph has no correlation, and the last graph has some correlation but not linear. Here are some properties of the linear correlation coefficient R. The value of R is always between -1 and +1. If all values of either variable are converted to a different scale, the value of R does not change. The value of R is not affected by the choice of x or y. Interchange all x values and y values, and the value of R will not change. R measures the strength of a linear relation. It is not designed to measure the strength of a relation that is not linear. R is very sensitive to the outliers in the sense that a single outlier could dramatically affect its value. Given any collection of a sample paired quantitative data, the linear correlation coefficient R can always be computed, but the following requirements should be satisfied when using the sample pair data to make a conclusion about linear correlation in the corresponding population of paired data. The first requirement is that sample of paired XY data is a simple random sample of quantitative data. Second requirement, visual examination of the scatter plot must confirm that the points approximate a straight line pattern. Third requirement, because results can be strongly affected by the presence of outliers, any outliers must be removed if they are known to be errors. The effect of any other outliers should be considered by calculating R with and without the outliers included. Round-off rules for the linear correlation coefficient R is that we round it to 3 decimal places so that its value can be directly compared to critical values, Table A5. When making conclusions, we use the following methods. If we use p-value, then if p-value is less or equal significance level alpha, we support the claim of linear correlation. If p-value is greater than significant level alpha, then we do not support the claim of linear correlation. If we use Table A5 to interpret the linear correlation coefficient R using the critical values, then if absolute value of R is greater or equal critical value, then we conclude that there is sufficient evidence to support the claim of a linear correlation. That will mean that the correlation coefficient R is located in the critical region. If the absolute value of R is less than critical value, which means it is not in the critical region, then we conclude that there is not sufficient evidence to support the claim of a linear correlation. Let's now look at the example. Remember at the beginning of this video, I mentioned the fact that police sometimes use footprint evidence to estimate the height of a suspect, and the height is included in the description that becomes part of a BOLO, be on the lookout. Around 1877, anthropologist Paul Topinard collected foot height measurements and used them to develop this rule. To estimate a person's height, divide their foot length by 0.15 or multiply by 6.67. Try it yourself by measuring your foot length and dividing by 0.15 to estimate your height. Is the result reasonably accurate? Anyway, we will use the data from Roar and Brenda, estimation of stature from foot and shoe length, applications in forensic science, to conduct a hypothesis test of a claim that there is a linear correlation between the two variables, shoe print length and person's height. So our first variable, shoe print, and height is our second variable. The null hypothesis is that there is no correlation between the two variables. The linear correlation coefficient of the population, pronounced as ρ, is equal 0, and alternative hypothesis is that there is some linear correlation between the two variables. Ρ is not equal to 0. We use alpha 0.05. Let's first use the p-value method. In the StatCrunch, go to Stat, Regression, Simple Linear. X variable will be shoe print, and Y variable is height. Leave this blank. Make sure alternative hypothesis shows the right sign, and click Compute. The linear correlation coefficient R is equal 0.813, rounded to 3 decimals. Let's write it down. And I almost forgot to check the requirements. So let's go back and check the requirements. To check the requirements, we'll need the scatter plot of this data. Click on the arrow to go to the next page. The first requirement is that sample of paired data is a simple random sample of quantitative data. Yes, the data are quantitative. Second requirement, visual examination of the scatter plot must confirm that the points approximately a straight line pattern, which they are. And the third requirement is that there are no outliers. Well, there might be a few outliers, maybe here, but this outlier will not affect the results. Or we can then recalculate it without this data value. So let's proceed. Let's go back and write down the p-value. The p-value is less than 0.0001. I'm going to write p-value is equal 0.001. It's so small compared to significance level of 0.05. P-value is significantly less than significance level of 0.05. Therefore, we reject a null hypothesis that there is no linear correlation and conclude that there is sufficient evidence to support the claim that there is a linear correlation between shoe print length and person's height. Let's now test our claim using the linear correlation coefficient. We found that the linear correlation coefficient R is equal 0.813. We will need table A5. You can find it in your course files, file called Formulas and Tables on page 3. Table A5 shows critical values of the Pearson correlation coefficient R. We will need a sample size. Our sample consists of 40 values. The critical value that corresponds to the sample size 40 and significance level of 0.05 is 0.312. Let's write it down. Let's now compare the critical value with the linear correlation coefficient. The critical value R, we use the absolute value of R, is negative 0.312 and positive 0.312. If the linear correlation coefficient is in the critical region, then we reject the null hypothesis. The linear correlation R of 0.813 is located in the critical region. Therefore, we reject the null hypothesis. In the same conclusion, there is sufficient evidence to support the claim that there is linear correlation between shoe print length and person's height. The line that best fits the points in a scatter plot of paired sample data is called regression line. The regression equation y hat equal b sub 0 plus b sub 1 times x is the equation that algebraically describes the regression line. The regression equation expresses a relationship between x, called explanatory variable or independent variable, and y, called the response variable or dependent variable. The equation of the regression line for sample statistic is y hat equal b sub 0 plus b sub 1 times x, and the equation of the regression line for the population parameter is y equals beta sub 0 plus beta sub 1 times x, where b sub 0 and beta sub 0 are y-intercept of regression equation, and b sub 1 or beta sub 1 for population parameter is the slope of the regression equation. Let's look at the example, how to find the regression equation using StatCrunch. To find the regression equation in StatCrunch, go to Stat, Regression, Simple Linear, the same place where we conducted the hypothesis test. Select X variable, shoe print, Y variable, height, compute. Here is the regression equation. Height, Y variable, is equal 80.93 plus 3.22 times the shoe print. Let's write it down. Y hat equals B0, the y-intercept of regression equation, plus B sub 1, the slope of regression equation, times x, independent variable, which in this case is a shoe print. Y hat is equal 80.93 plus 3.22 I'm rounding to 2 decimals, times x, where y hat is the height of a person and x is the shoe print length. Y hat is dependent variable and x is independent variable in this case. Remember, if we switch the values, the equation will be the same. Now, for example, we want to find what would be the height of a person if the person's shoe print length is equal to 30 centimeters. Well, let's see. Then y hat will be equal to 80.93 plus 3.22 times x is 30 centimeters. Use your calculator. The height of a person who has shoe print length of 30 centimeters is equal 177.53 centimeters. If you want to convert it to standard system into feet and inches, and you forgot how to do that, watch my video, Conversion between Metric and Standard Systems of Measurement, in the playlist JB-AVC Basic Math Concepts. I hope it was helpful.